Okay, this is a solution to number 15 on the energy problems. It says that we have an object that has a mass of, okay, the mass is 0.5 kilograms. And during its motion, okay, and it moves from, okay, so let's just visualize what's happening. Um, there's, space, it's moving in a plane, and it starts out at 1, 0, and it ends up at 410, so something like that. Um, we don't know what path it follows. Could be any crazy thing. It doesn't matter. Um, and the reason it doesn't matter is what it says next. Three forces act as it goes through that motion. Okay, so this point is, I knew that was going to happen. This point is 1, 0. This point is 410 in meters. And three forces act. A normal force as it goes through its motion. So it's sort of rolling or sliding along a surface. And then that's a non-conservative force, but it does zero work. So that means that if no other non-conservative forces do work, we can still use conservation of mechanical energy. The second one is a potential energy function. So that's a conservative force. That's potential energy is defined by 5x squared minus 2x. And the third force is another conservative force with a potential energy function of negative 6y. So you could think of these, I mean, we don't know what these forces are, but you could think like, they're things like gravity and spring forces. They're forces that only depend on the object's location, and the potential energy function is defined by this. Okay, and the first thing we want to do is calculate the total work. Well, so the total work is the work done by the normal force plus the work done by that first conservative force plus the work done by that second conservative force. This one is 0. And so all we have to figure out is the work done by these two potential energy fields, these two conservative forces. Well, remember that work is equal to the negative change in potential energy, which I'll call it capital U. Okay, so we can do them individually and add them up, or we can think of this as the negative change in the sum of these potential energies. It's the same, gives you the same answer. Okay, so at the later instant, I'll call it instant 2, the position is 410. And so U1, we're just going to plug those coordinates into the U1 function. So that is 5 times 4 squared minus 2 times 4. And so that's 5 times 16 minus 8. So that's 80 minus 8, so 72. We'll assume that this is all in SI units. The position is definitely in SI units. U2 at instant 2 is negative 6 times the y coordinate. So negative 60. There's nothing saying that potential energy can't be negative. And so you can think of the U, the total U at that point is the sum of those two. So 12 joules. And at instant 1, the position is 1, 0. So plug that into the U1 function. You get 5 times 1 squared minus 2 times 1 is equal to 3 joules. The second potential energy function at the point 1, 0 is negative 6 times 0, so that's 0. And so U total is 3 plus 0, so 3 joules. The change in U is the total U at the later instant minus the total U at the earlier instant, so 9 joules. And so the work is equal to negative delta U, negative 9 joules. So that says that as this object travels through this path, energy is removed from the object. And the work energy principle says that it's moving more slowly at the end than at the beginning if energy is removed from it. So you can see if you do have these cases where you don't have any work done by non-conservative forces, you have this pretty powerful tool where you don't have to know anything about the path. You can calculate the work done and use conservation of mechanical energy to calculate the speed just based on what you know at the beginning and the end of the path. That's at least one of the really key strengths of the energy approach to problems. Part B, what's the change in kinetic energy? Oh, well, we just calculated the work energy principle says that the work done on an object is equal to the change in the kinetic energy. And so the change in kinetic energy is also equal to negative 9 joules. Well, that's the change in 1/2 mv squared. So we can also figure out things about, changes in speed based on this. And that's what the third question asks. If the problem initially, so let's say the speed at instant 1 is 10 meters per second. Then that means that the kinetic energy at instant 1 is 1/2 times the mass, which is also 1/2, times the speed squared. And so that's 25 joules. And it asks, what's the object speed at the end of the motion? Well, the change in kinetic energy, which I think I also denote often as change in like a fancy T, because we're not really used to using multiple letters as variables. This is sort of a more mathematical way to write it. Okay, that's equal to, well, we know that it's equal to -9 joules, right? And that's equal to the kinetic energy at the end of the motion minus the kinetic energy at the start of the motion, which we already know is 25. So -9 is equal to 0.25 v squared minus 25. And so 16 is equal to 0.25 v squared. So 64 is equal to v squared. And so v is equal to plus or minus 8 meters per second. It's a speed, so we want the positive. And so based on that information, we can calculate the speed at the end of this motion. Well, in some cases, you could go through, I mean, actually, you could go through and derive all these equations from Newton's second law. So in that sense, you can use Newton's second law for this. But for a problem like this, it'd be really complicated, and you'd end up, like the way we tend to think about this stuff, you'd have to know something about this path so you could calculate the forces. You know, you could, from the potential energy functions, you could use those partial derivatives to find the force at each location. And then you could integrate it over the path, but it'd be a horrible mess. This is just a nice, clean way to calculate this stuff. And remember that the key is we were going from a change in an object's position to a change in an object's speed. And that sort of needs to be the thing that clicks the switch in your head that says, I probably want to try energy with this. Well, the other thing that says that is that this is number 15 in a set of problems that says energy at the top. But, you know, when you see these problems like this in a test or in the real world or whatever, that's sort of the hint that energy might be a good way to go.